Okay, so thanks everyone for coming on today for another one of our HSMA showcase sessions. Particular thanks to Elliott, who at the 11th hour has stepped in. So Tom was due to give a talk today on some of his forecasting work. I think Tom has forgotten because Tom has been in America and is not responding. So we decided we'd better have a backup plan. So Elliott's very kindly offered to bring his talk forward that he was due to give in February, which I think actually will be quite useful because some of the things he's going to talk about will be useful when you're thinking about formulating your project ideas over the next couple of months. So hopefully this will be really interesting for you. So I'll hand over to Elliott, who will give you a bit of a talk, and then if there's any questions afterwards, please just let us know. Fantastic. Thanks, Elliott.
Great, thank you very much, Dan. A couple of apologies to make in advance. One, for some reason, my internet is a little bit unstable today. So Dan's agreed to let me know if you can't hear me for any duration of time. And the other thing is you may hear a dog barking in the background. I've closed the door, put the suitcase in front of it so we can't scratch. I do apologise in advance for that, but the joys of home working. So thanks a lot for coming along today. As you may have noticed, even quite recently, there was another change to the advertised topic. And this is probably just a little side note for everyone to have a think about. When you come up with your project proposals, it is really worthwhile making sure that everyone, all of the stakeholders, anyone that's going to influence or touch is aware and is on board. With my project, I was originally going to do a demand and capacity model for an emergency department. But 3 weeks into the project, we actually had done all the exploratory data analysis. We went and talked to the people from ED and they said, because of COVID, we've rejigged the way we've worked, which I'll be talking about, and we don't need that. Can we do something else instead? And that's how I ended up on the project I'm on. So it is really worthwhile making sure you've got sign off and people understand what it is you're proposing to do, because there'll be nothing worse than you starting a project and then it having to pivot drastically because one of the stakeholders or someone of influence isn't on board. And these things will happen. They're sent to test us. And I think, a lot of you will probably have had these problems in the past and you just learn to roll with it. And there's nothing wrong with that, but just be prepared and do as much work as you can in advance, especially if you've got some really big, lofty ideas for the project proposals. Anyway, just to give you a bit of a background, part of the MSc that I know Dan has mentioned a couple of times that I did prior to joining the HSME team. We have 2 sets of 12 weeks of teaching, so just standard lectures, and then we move on to a research project, which runs, I went from May till August, and it's worth about a third of the overall marks of the MSc. And with this, we work with real-life organisations, and for myself, I worked with the Royal Cornwall and Hospital Trust down in Truro. So I was within the info services team, and I was working on a project specifically with the emergency department. And what I wanted to use, or what I wanted to establish to help them, really, they made some changes due to COVID within the department, is what factors were influencing the clinically ready to proceed time within the department. Don't worry if you don't know what that is, I will be explaining it all as we go through. So the aim of the project, as I said, is to understand what factors are influencing this particular timestamp. And to do that, I was going to use a machine learning model. Now, just think, usually machine learning models are made for predictions, but as you'll remember from Anna's talk the other week, they wanted to look at what factors influenced the prediction that was made. And I was more interested in this middleware as opposed to the final output. So to do that, I had to go through and understand the available data, then had to identify, well, which machine learning models would be suitable for this purpose. Then, as we'll be doing with forecasting, actually compare the performance of the model against just a naive forecast. So I used a rolling 3-hour average as well as just the average value to see or make sure that it was better and it was actually worth doing all this work. And then once I'd identified the best performing model, I then wanted to look at the feature importance and then report that back to my stakeholders. So for those who may not be working within health, you may be wondering, what is this clinically ready to proceed time? And to illustrate it, I'm just going to talk you through a patient's standard journey through an emergency department. So a patient will arrive. They can arrive by foot, by car, by taxi, but they can also arrive by ambulance. They are then, usually within 15 minutes, triaged by regularly a nurse. And the whole idea is to assess kind of how urgently they need to be seen. After triage, they are then seen accordingly. So a major trauma case would be seen very quickly, as opposed to someone who's gone in with a severe cut on their finger. They're then seen by a doctor or the relevant healthcare professional. And then a decision is made that they are ready to proceed. Now, that can be they're ready to go home. They need to be admitted into the hospital. They need to be transferred to another department for further investigation. But basically, it's that time point of which there's within the control of the department that I was looking at. Because after that first decision is made, this person doesn't need to be here. They need to be somewhere else, whether it be home, upstairs, whatever. Then, this is out of scope from that point on. The reason being, it may take time to organise patient transport to get them home. It may take time to find a bed to put them in upstairs. And those factors really are not the responsibility of the department, and they have very little control over them. That's, their ecosystem. This is to do with the wider hospital or even the wider world. So as I said, I'm only interested from that time when they walk through the door to the time that they're first assessed as, right, they don't need to be here anymore. So first of all, it was important to understand, well, what are the spread of these clinically ready to proceed times? So this is a frequency distribution graph. And I was looking at 12 months worth of data, and just to put in the side of your mind, this was still running, up until I think the end of March of this year. So still factors, COVID and the changes to workflow were all still influencing it. So it may not be the same as it would have been in 2019 prior to the pandemic, but ultimately you can see distribution, it increases the frequency up until just before the 4-hour mark, because there's a standard measure that people should be seen within 4 hours when they go to an emergency department. So as you might expect, lots of people are seen before that point, then there's a huge drop off, but then there are still a significant number of rats and mice. The average or the mean CRP time was 199 minutes, so just over 3 hours. And you can see here, I've shown most of the results, but 0.5% were over 10 hours that they were waiting. With a maximum of 1,751 minutes. So I can't do that off the top of my head, but a long, long time. And unfortunately, just to process flows through the department and having to segregate people with positive COVID, negative, and those unknown, it was really affecting how fast patients could be seen. And even, when I first arrived in May even, there was loads of ambulances parked outside, and people would arrive in the ambulance and someone would come out to triage them, but they couldn't physically put them into the departments because there was nowhere to put them. So that was also having an impact as well. So lots of things going on, hence the need for the project. So to select the model, had to really think about what was the objective and what were the features. So the great thing was I had an amazing data set, and it had 33 different feature types. And they were categorized as attendance specific. So these are kind of patient level data. So what acuity was the visit, what day of the week, the time of the day, and what was the time taken for diagnostic tests. And so here I bundled together either pathology, so blood test, or X-ray and imaging. They were just bundled as one. And then as well as that, I then had aggregated values as well. And these were departmental and workforce info. So the number of patients physically in the department in the 1 hour block with which the patient arrived, as well as the staffing mix. So for the staffing mix, I was able to work out for each 24 hour of the day, how many junior nurses, senior nurses, junior doctors, F2, so on and so forth. And so we knew kind of what the staffing mix was compared to the patient mix, with the idea that that may have influenced the speed. So maybe if you have more senior doctors on, the people will get seen faster than more junior doctors, or so on and so forth. And ultimately, the model was going to be used to predict a continuous variable. So what that means, I wanted to put in these features and then predict a number. So based on all of this, I wanted to tell me how many minutes the CRP time would be, and that could be 175 minutes. So with all this in mind, the potential models on offer were a linear regression. Now, really, there's far too many features for a linear regression. That just really wasn't going to work. Then there was tree-based models, of which there were random forest and XGBoost. Now, these seem pretty logical, and we'll talk more about these in the future on HSMA. As a pretty logical approach, that was good. And then there was ultimately neural networks. Now, neural networks probably would have come up with a really good prediction. However, we wouldn't really be able to easily identify what was happening within the model itself. It's a bit of a black box. And as Anna was talking about with explainable AI, we need a model that we could, look inside and figure out how the model's coming out with a prediction, because I'm more interested in what's happening in the middle than the final number. And so with that in mind, the random forest and the XGBoost models were the ones that I was going to assess against the naive benchmarks. And so with that in mind, once I got the best performing model, which was XGBoost, similar to the charts that I know that Anna showed, I'm looking at a single record here. And unfortunately, I haven't been smart enough to invert it like she had. But if we start by looking down at the bottom of the screen, we've got this expected value. And this was actually just the mean value for the validation data set. And we can see here, it was 198 minutes. Then ultimately, for this particular patient, the final estimate that the model spat out was 363 minutes. And this shows us what factors influenced, how did it get from that expected or the mean through to the final prediction. So you can see here, kind of in descending order of importance for this one person, because it does vary, you can see the time taken for their test was nearly 3 hours, 175 minutes. And that had quite a big impact. That contributed quite a lot to the model saying, well, I'm taking the mean and I'm going to move it up to 363. You can also see the time taken to triage the patient, 28 minutes. Well, again, that also had a positive influence. Now, interestingly, the patients awaiting a decision, so these were patients undergoing active investigation. At the start of the hour, there was 36 of those sat in the department, and that actually kind of took the prediction down a little bit before then looking at the average time to care in the previous hour, which was nearly 330 minutes, and that again had a positive impact. So you can go on and work through, and so now we know for this particular patient or this particular visit, how do we end up with the prediction that we did? Then if we look at overall, so this is kind of looking at all the predictions and the impacts that the different variables had, we can see here, if we look at the time taken for tests, so again, this was pathology, blood test or imaging, x-rays and what have you, the range of values we saw within the data set was from 0, they didn't need a test done, through to 1483 minutes. And so the blue dots, so this is like a swarm plot, the blue dots represent lower values, where the red dots are higher values. So if I'll just move on to the next one, makes it slightly easier to see. So you can see those that had low values for time taken for tests, including 0, well, that actually had a kind of a negative impact. Remember the way we looked at the waterfall plot on the final prediction, whereas those that took longer for their test to be carried out actually contributed to a higher CRP time prediction from the model. And that even works if you look down at this fourth measure here, departure group method. This was discharged, this uses one hot encoding, so it was binary. It was either were they discharged, 1 or 0, the other options being admitted or so on and so forth. And so you can see here that those who were admitted, that always seemed to have a more positive impact. And that could be because, they were more ill. And so the fact that they required admission meant that they needed more investigation before that decision was made, or whatever it happened to be. So that's great. We've got the model. It's made predictions, and we can understand how the predictions are being made. But how did they actually perform? Because this is also very, very important, because it also tells us, can we hang our hat on the insights we're getting from it? So as I mentioned earlier, we looked at a rolling 3-hour mean. And so this is just no machine learning. I've just literally what was the average clinically ready to proceed time for our test data and our validation data. Now, you remember Dan talking about our different metrics previously. So we've got mean squared error, root mean squared error, mean absolute error, and mean absolute percentage error. I was most interested in the root mean squared error, just because it had units of measure that were kind of equivalent to what I was talking about, i.e. minutes for the predictions. But I just put them all in for illustrative purposes. So you can see here that we were looking in the test data, 117 minutes, and validation 114. So it doesn't look like it was overfitted, which is great. Next, if I just looked at the mean across the whole data set. So for the test data set, it was 107 minutes versus 104 minutes for the validation data set. Again, that's an improvement, which is strange because you would have thought of rolling through our mean, given that the department is busier at certain times of day, would have been better, but it wasn't. Then when looking at the random forest, there was an improvement again. So the error reduced down to 87 minutes and 87.4. But then when we look at the XG boost, we reduced even further across all measures. And you can see that was down to 77.5 and 75.9. Now, if you're making a prediction in minutes and something's out by over an hour, probably not going to be that excited by it in reality. So I wouldn't be using this to predict CRP time. But the fact that we did get some useful measures out of it was quite important for the department. And so what I've got here, I wanted to compare the distribution of times of the actual CRP times for the data set against the predicted. Now you can see here, for the longer times, the frequency distribution matches. However, it looks like the model, when it was predicting the CRP times, it had a tendency to increase them somewhat. And you can see that here by the blue line being to the right of the orange, but then obviously the area under the curve will be the same. However, it's kind of shifted to the right. So, you know, we can see it's not perfect, and that's fair enough. But one of the what if scenarios was, and this was, again, not hanging our hats on this, but it was just something to consider, is, well, you know, we saw that the time taken to undertake tests was an influential factor. What would happen if across the board we could increase that time or make it 10% better? So again, bear in mind, our prediction is not perfect. We've got here, the orange line is now the predicted clinically ready to proceed time. And you can see it had a mean 199 minutes and a median or middle value of 189. And with it fast, so basically I kept all the other factors the same and then reduced any testing times by 10% and pushed it through my model again. And you can see here that there was an improvement. So the mean time, the mean clinically ready to proceed time decreased by 12 minutes, and then the median was down by 4 minutes as well. So that potentially said to us, could you increase testing time to reduce the CRP time? Now, interestingly, this actually correlated with the literature, and lots of work being done in the wild, you know, both in the UK and the US, and it's been published, saying, well, if you prioritize pathology tests, you can do this, you can do that, and it does increase things. But it'd be quite naive to think we got to 2022 without all of these things having already been implemented within the department. So the conclusion really for the project was that the XGBoost model was superior to a naive benchmark. The most important factors were testing time, number of patients awaiting a decision, and triage. Now, this is interesting because there's a lot of chatter, a lot of evidence to say that crowding within departments can actually have a negative impact on overall care, and CRP time being a factor of that. But with that, we would expect to see total number of people in the department. So those undergoing active investigations, so awaiting decision, plus those who are just sitting around waiting for a bed to come or an ambulance to take them home, by virtue of more people in the department or more people in a confined space just makes it harder for those who are working to navigate their way around and find somewhere to put the new people and so on and so forth. So this insight was interesting. And whilst this was not a definitive causal inference model, the interpretation, is going to be useful for them in verifying and disproving some of the assumptions like overall crowding. Now, operationally, it's likely the department's still running atypically due to COVID. And the training data consists very high and low COVID numbers in the community, and all, that was all to do with restrictions and lockdowns, and also the way the department operated. So they were trying to deflect minor patients to urgent treatment centres. So this kind of variability throughout the time period may have had an impact. And so if I could revisit it again, I'd probably want to break it up into smaller time chunks when kind of there was a consistent approach to COVID in that time. So the next steps, anyone thinking of doing something similar, the other things that you could consider for a piece of work like this would be to add flags to say, was the patient medically or surgically expected? Had they been pre-warned, or did people know that they were about to attend the department? Did that impact the CRP time? What time of presentation was it? Were they at readmission? Were they a frequent flyer? Had they been in about this problem previously? And then that will help identify who requires less time, someone fresh or someone who's been in previous before. Then, as I said, it was a very rough and ready assessment it did of improving the testing time. But we could just say, well, what if all tests were completed within X mins, finite number? Did that cause any great improvement? And then, if we said, testing time over a certain amount, if that got reduced, could that make improvements as well? Again, this is a great way to play in a sandbox without actually making any changes to practice to see if it's likely to cause any impact, because you don't want to rejig a whole pathology service that supports an ED only to find out, oh, it didn't work in reality. You've got to be quite sure before you make operational changes. And this is a great way to do it without impacting patient care, which is obviously the most important thing of all. And the other thing that could be done to increase the accuracy of the model, we've gone for a continuous variable. So we want to predict 170. What if we broke it into time bands and said 0 to 30, 30 to 60, so on and so forth, and make it a categorical, a classification model? That may improve the accuracy. However, we're looking at why we're doing it, and it's great that it may be more accurate, but under the hood, we're still looking at what factors really influenced the final decision. So the value of that is potentially somewhat limited and flawed. Anyway, that's it for the presentation. Obviously, if anyone's got any questions, I shall do my best to address them. Thank you.
Brilliant. Thank you, Elliott. Thank you very much. Really interesting, an interesting use of machine learning, actually, to, as you say, for that kind of explainable, to look under the bonnet and try and work out, well, what is going on? Are these, are our assumptions correct? I think it's a really, really interesting use of that. So any questions for Elliott, please?
Yeah, I've got a question. Can you hear me okay?
Yeah, I can hear you.
Okay.
Yeah, it's Tony in Reading. Thanks, Elliott. That was really, really good. Just a quick question on one of the later slides that you put on. I think one of the factors you said were important was triage time, and I just wondered, was that actually just correlated with the volume of arrivals rather than being its own sort of particular factor? Because we find as it gets busier, triage time, time to decide, and time to discharge all increase sort of monotonically with patient arrivals, and I just wondered if that was the case for this data set as well.
Yeah, absolutely. I mean, I would have to kind of go back and look at the numbers in more detail, but as my memory serves me, bear in mind this was all put to bed in late August. When looking at the correlation matrix, which is obviously one of the steps you do as part of the exploratory data analysis, that was, I believe that was the case, yes.
Great, thank you.
Which again, it goes back to the whole crowding, doesn't it? The number of people physically in the department just has this flow-on effect everywhere.
Yeah.
I've got a question, Elliott.
Sure.
Really like the presentation, thank you. The question is, so you found that the more crowded or the more patients were waiting for decision, the less time they spent waiting. Is that right? Is that if I understood correctly?
Oh, sorry, can you say that again?
So the more patients were waiting, actually that reduced the time spent waiting.
One input. So this is literally one prediction that was made, and in this situation, it's just looking at how the model came to its end, the number it came out with, and this one saying, well, there was 36 patient decision. In this instance, that actually had a negative impact. That could be because on average, there are more patients, usually the department has a lot more patients physically present awaiting a decision.
Yeah, I was just thinking, if there's one patient waiting, a senior decision maker isn't going to step down from whatever it is they're doing to make those decisions. Whereas if there's a lot of people, they might, so, you know, prioritize that as their task in terms of task. I'm not sure. It's really interesting. The time taken to tests is that distribution has got like three very distinct like phases. I don't know what to call it. Sorry.
Yeah. So this, because they're like a swarm plot. So basically, each one patient or one prediction is one dot and the values that had. So you can see here basically what that's saying is the people that had or the predictions that shared a decrease from expected value to the prediction, there was more of them that had this negative value of 50. And it just so happens that they all shared a very, very similar, their testing time was quite similar, and it was quite homogeneous. So for example, you'd imagine all of these people, all the testing time was 0, i.e. they didn't have a test. And then as the color increases and gets, to more, to a high color of red, the value is higher. And so there's lots of people here, quite a few people here, less people here. And I don't know if I'm explaining that particularly well.
No, you are. Thank you.
Yeah. Okay.
Hi, Elliott. I was wondering the model seems to be quite good at predicting the ones that wait the longest. I mean, the test and the validation, they quite almost on the top of each other. Is the ones that a decision is made quicker, that there is a slight discrepancy. Is that because when you look like your violin plots, time taken is the one that actually goes beyond 2 minus 100 or so, all the other distributions. So do you think probably don't have enough information or enough features on that time frame, where those features are really important?
I'm just making sure I understand the question correctly.
When you look at your distributions, the predicted and the real ones.
Yeah? Oh yes, sorry. Yeah.
Yeah, this one. Yes. Okay. The discrepancy is early on. Yeah.
Yes.
And I'm wondering whether here you don't have enough discriminating features.
Yeah.
And that's why it's so much better than the late ones, because on that time frame that is, quite short on that decisions are taken.
Agreed. But also remember, it's interesting how the RMSE, so the error measure was 70 odd minutes. Well, that's that's probably accounting for that difference.
Yeah, that's right. Yeah. That makes sense.
So yeah, I guess maybe if we separated out those who had tests and then had the distribution of that, and those who did not have tests at all, maybe separating the data set like that could be more. But then again, with the tree-based model, it wouldn't make a difference. So potentially more features could be cooked up, but we came up with as many as we could, and also as many as we had access to the data to support. And that's something else to consider more broadly in a message for everyone. Make sure that you're going to be able to get the data that you want in a timely manner, and the quality is going to be sufficient that you can use it and hang your hat on.
Yeah. Thank you.
Just to, Toby, I think you've had your hand up for a while, so I'll make sure you come in there.
That's all right. Thank you. Thank you, Dan. Thank you, Elliott. That was very interesting. Interesting because certainly we're finding, and we're concerned that over testing is a potential impact on the department. So I don't know whether the department you looked at is actually changed their testing regime as a result of that. No, I saw that.
No, there has been, as far as I'm aware, there's been no operational changes. And as soon as I said, "Oh, testing time," they were like, "Yeah, no, we're happy with that." I believe they'd kind of optimized it within the recent past, and so they were happy. There was no appetite to change it. And again, it's always interesting when you feed these insights back to stakeholders. what's their opinion, what's their take on it? Because there's, I'd only just arrived at the trust. I didn't know what had gone on there historically, what changes they'd had, what arguments or not, or what the personalities involved. You don't know how it's going to, your intent and how it's perceived are two very different things, and how it's, how it lands a particular message. But that's really interesting, and I'm trying to figure, how would you work out if there's too much testing?
I guess I mean, as I say, that's certainly something that we're looking at. And I also wanted to check with you, when you describe something as testing, did you take the broad spectrum, anything from taking bloods to doing a CT scan? Did that all
Correct.
count as testing? Yeah.
And that was just to go back half a step. We'd had that slight hiccup at the beginning of the project where we had to pivot for the new direction. And then our target variable, this clinically ready to proceed time that we were getting out of the back end of the AS system, the patient administration system, the predictions were garbage. Like it was coming out with wild numbers. It was, I couldn't have done anything with it. Literally would have just had to put it in the bin. But luckily, one of the very senior doctors there was actually very involved with the data team, and he knew the SQL table structure behind it. And he said, "Oh, no. The way we use the system, we click on this button a few different times, and we had been looking at the final timestamp and not the first timestamp." So he said, "Do this." So it was actually quite near the end that I actually got a model that worked. And it was then when they said, "Oh, why don't you do testing time?" It was just literally the fastest and easiest way to get the testing time was to bundle it together. In an ideal world in Nirvana, we would have it, and you'd imaging, test it, and you probably further make it more granular again. And what type of test was it, and what combination of tests was it? In an ideal world, yeah. But for me, it was just like, right, it has to be quick and dirty. Because of where we are on the timeline of the project. Because again, there was a hard end date with the project submission.
Yeah, and I'm assuming, my last question, but I'm assuming from your previous answer, I was going to say, did you differentiate, say, between majors and minors patients, and was there any difference? But I assume from what you said, you probably didn't have time to do that either. Yeah,
look, the interesting thing was that most minors, there wasn't a lot of minors patients in the department. Basically, they were getting referred to an on-site UTC run by 2 GPs, or deflected back into the community to go and see a regular GP. So the data was very heavy, imbalanced, if you might say, for major patients. But there were still some minors creeping through, at times of the day where they couldn't go and see anyone else. And it was, yeah.
Right. Thank you. That's
no
really
problem. So yeah, so minor accidents and and minor illness were sent on the way.
Cheers.
No problem.
Thank you. Any other questions for Elliott before we close? No. Okay, well, in which case, thank you again, Elliott, especially for, that was a fantastic talk on its own merit, let alone me sort of messaging you at 10:30 last night and saying, "Do you mind doing this?"
Not a problem.
Because I can't get hold of Tom. So fantastic, thank you. And hopefully that's given you all lots to think about when you come to your own project as well. I think lots of learning from that, and a really interesting use of machine learning, I think, there for something that's so timely and important to so many trusts at the moment. Brilliant. Okay, thank you, Elliott. Thank you everyone for coming. Those of you who can make it on Tuesday, we will see you on Tuesday afternoon for your bring your own agent-based simulation workshop, where we'll have a bit of fun for the last session before Christmas. If I don't see you before, have a great Christmas though, and we'll see you in the new year. Brilliant. Thanks everyone.
Thanks.
Thank
Thank
you.
you.
Bye.